Hello, grade 7. So this is lecture 3 out of 3. So this is the last lecture about chapter 2, which is mass. Okay, so let's start. Now, the objective that we're going to cover during this week's lecture is that you guys will be able to distinguish between mass and weight. So let's start. Now, before we start with the weight and the mass, we have to review, this is the last lecture about mass. So we have to review everything we've learned about mass so far. So let's starting with the units of mass. So we said we have ton, kilogram, gram, and milligram. I did say like 1 ton is equal to what? Is equal to the mass of a car, right? How about a kilogram? How much is a kilogram? How about 2 pineapples? How about a gram? It would be the mass of $1 bill. And a milligram, it is the mass of 1 grain of salt. This is how small this unit is. Now, how do we convert from one unit to the other? From ton to kilogram, I multiply by 1,000. Kilogram to grams by 1,000. Grams to milligrams by 1,000. Now, the other way we divide. So from milligrams to grams, divide by 1,000, and then we divide by 1,000 and another 1,000. Now, what if I want to convert from ton to milligrams? So as if I'm going 3 steps. 1, 2, 3. So I multiply by 1,000, and then another 1,000, and then another 1,000. And what if I want to convert from grams to ton? I go 2 steps. I divide by the first 1,000 and then I divide by the second 1,000, right? So I divide by this first 1,000 and then the answer I also divided by another 1,000. So having a quick review about how to measure the mass of a solid. So first of all, we calibrate the two-arm balance to have equilibrium when both arms are empty. You can see that it is pointing at 0. It means it is calibrated well. And now we put the solid on one pan and then we put some labeled masses on the other pan until we reach equilibrium, until the needle just points to 0. And when that happens, when equilibrium is reached, then the mass of the solid and the total mass of these labeled masses would be equal. Hence, we would have measured the mass of the solid. Now, in the liquid case, we said we can't just pour liquid on one pan because it will spill and we won't be able to measure its mass. So liquid, we need to put it in a container, in a beaker in this case, in any container. So first of all, we measure the mass of the container. So we put labeled masses on the other pan until equilibrium is reached and we measure the mass of the container. And then we fill this container with the liquid, and then we measure the mass of the container and the liquid. Okay, so we put labeled masses on the other pan until equilibrium is reached. So we have the mass of the filled beaker now. And to find the mass of the liquid inside the beaker, we simply subtract the mass of the filled beaker minus the mass of the empty beaker. We will get M, which is the mass of the liquid inside the beaker. Now, moving on to the last section in our chapter, which is weight and mass. So I'm going to ask you to do something, okay? Hold any object with your hands, okay? Just hold up any object, something that won't break, okay? Like maybe a book. Now, let go of that object. Let go of the book. What will happen to it? It will fall to the ground. Why is that? Don't you ever wonder why things fall when we simply let it go? Like, why do they fall to the ground? Why don't they fall, I don't know, upwards? Why downwards? What is happening? This is actually due to the action of the attraction force exerted by the earth on this object. So something is actually pushing this object down, something, yeah, so that's it. This is the force of attraction that the earth exerts on this object. What do we call this force? We call it the weight. So the weight of a body is the force the earth exerts on that body. Okay, so this is weight. Okay, so it says here, hold up an object of mass m equals 1 kilograms. So this is an object, okay, of mass 1 kilograms. Let go of that object. The object now simply falls to the ground under the action of an attractive force the earth exerts on that object. What do we call that force? We said we call it the weight, right? So the weight of the body. Okay, so this force is called the weight. Hang that object to the hook of a dynamometer. So this is a dynamometer. It is an instrument used to measure the weight. Okay, so we have the mass is measured using a balance. It could be a digital balance or a two-arm balance. Okay, now the dynamometer measures the weight. As you can see, its hook is empty now. Okay, nothing is hanged here. When we hang the object, which is 1 kilogram, we end up having a certain value here, which is approximately 9.8. Now, what is the unit of this value that this value is expressed in? Can you see a unit here? I see like different numbers. It is graduated, but I see in here a capital N. Yes, so the unit is, we call it Newton. Its symbol is capital N. It says here the same experiment. Now this experiment is performed in Lebanon, okay? So this one is in Lebanon. The same experiment is performed now in what? The same experiment is performed by a student that lives at the equator. So I have a student living at the equator. The dynamometer indicates 9.78. So it indicated a different value. What can we conclude? That the weight of a body varies from one place to another, right? Because in Lebanon, it indicated 9.8, but at the equator, it is 9.78. So we say the weight of a body simply varies from one place to another. So, first of all, we need to remember that a dynamometer, or we call it also a spring balance. So it has two names, dynamometer or spring balance. It is an instrument used to measure the weight of the body. And its SI unit, the weight's SI unit is Newton. Okay? Okay, so let's see what we can do here. We hanged an object, a 1 kilogram object, on a dynamometer in the North Pole, and the same object was hanged from a dynamometer in the equator. What we notice is that at the North Pole, the weight is 9.83 newtons, whereas at the equator, the weight is 9.78, so it's not the same. As we said, weight varies from one place to another. So the weight decreased. So it decreased. Okay, the weight decreased going from the pole to the equator, and it increased It increases going from the equator to the pole. How about the mass? We're talking about weight here. How about the mass? Let me put the 1 kilogram on a balance. So it gives me 1 kilogram. Let's put it on the equator as well. Oh, it also gives me 1 kilogram. So the mass is constant. Okay, it does not change from one place to another. It does not vary from one place to another. So we can say that the mass of an object is constant, while the weight of an object varies depending on the location of that object. So it's so important to know that mass is constant. It doesn't change from one place to another. But the weight, it does. Now I'm going to use this simulation to show you how weight and mass behave on Earth, on the moon, and on different planets. Okay, so let's see. This is a dynamometer, and I will put the watermelon on the dynamometer, and we are on Earth. Okay, so it says here Earth. So the weight of this watermelon is 96.6 newtons. Okay, now let's go to the moon. Whoa, the weight changes. So it was 96.6, now it's 16. If you actually use a calculator, you would see that it is 6 times less. Okay, now let's go to Mars. The weight is 36.5 newtons. And let's go to Jupiter. Whoa, the weight is 244.2 newtons. So the weight differs from one place to another. It differs from one planet to another. And even if we are still at Earth, it differs from the equator to the North Pole to any other place on the planet. Whereas the mass, let's try the mass. Let's try it with this little ball, right? We knew that its mass is 150 grams. So this is on Earth. Let's see on Moon. Oh, it's the same mass. How about on Mars? Same mass. And on Jupiter? Same mass. So the mass is constant. It does not change from one place to another, but the weight changes from one place to another. So if I have an object hanged from a spring, okay, this object is of 1 kilograms, it will give me a weight of 9.8 newtons. Now, if I took this dynamometer and the object to the moon, as I said, it will be 6 times less. So I simply divide 9.8 divided by 6, and the answer would be 1.6 Newton. Okay, so this is the weight of that object on the moon. So the weight of an object on the moon is 6 times smaller than its weight on Earth. How about the mass? If I have an object and I put it on a balance, it would give me 1 kilogram because this is a 1 kilogram labeled mass. Now, if I took this balance with the object to the moon, it will also give me 1 kilogram. Okay, so this means that the mass does not change from one place to another, it is constant. Now let's put what we know about the mass and the weight in a table. Okay, so the mass of symbol M and SI unit kilograms, weight of symbol W and SI unit of Newton. The mass of an object represents the quantity of matter that the object is made of, whereas the weight of a body is the force that Earth exerts on that body. The mass of an object doesn't vary from one place to another. It is constant. The weight of an object varies from one place to another. The mass of an object is measured using a balance. The weight of an object is measured using a spring balance or a dynamometer. The SI unit is kilograms for the mass, and the SI unit is Newton for the weight. So that is it. We just finished the entire chapter now. I hope you guys understand this very well. You can go and solve the worksheet now. I'll see you in the Zoom live. Take care and bye. Bye. Bye.